Hey everybody, Corey and Victoria here. We are the Professor's Du Bois, and in this lecture we're going to talk about heat transfer from a chemical reaction to the surroundings and how we measure that.
And we measure that using a type of experiment called calorimetry. There's a couple different types. One is at constant pressure, which means it's usually done just in the laboratory, open to the atmosphere, and it's at atmospheric pressure, or a constant volume calorimetry where it's in a vessel and it's held at constant volume, and we call that the bomb calorimetry method.
So in this lecture we're going to talk about the constant pressure calorimetry. And when we do constant pressure calorimetry, the heat evolved or absorbed, could be an exothermic, could be endothermic, during a chemical change is measured under conditions where the pressure is not changing. So we're open to the atmosphere. The heat evolved or absorbed could be endothermic or exothermic. We're calling heat Q. It's equal to the enthalpy change for the reaction, and we call that delta H.
All right, so coffee cup calorimetry really is representing this constant pressure calorimetry, and it often consists of coffee cups, styrofoam coffee cups, and they're nested together so that we can minimize loss of temperature, loss of heat or energy, and we cover it with a lid, and we can measure the temperature within it, and we measure the before and after the reaction and see how our solution inside of it changes temperature.
So we have to identify what's the system and what's the surroundings. And the system in this case is the chemicals undergoing the change. And a lot of times when we do this, we'll dissolve ionic compounds in water. So the dissolving of the solid would be the solid would be the chemical that's undergoing change. But we can also do chemical reactions inside of the coffee cup. So the surroundings are what we call the other contents of the calorimeter. So it's often water, going back to dissolving a solid. We'll dissolve it in the water. That water is considered the surroundings. The calorimeter itself is part of the surroundings and all of the materials around the calorimeter.
So like I mentioned, it's nested coffee cups. So we're using styrofoam, we're minimizing loss of the temperature, and in fact we're assuming that the calorimeter in coffee cup calorimetry is not absorbing any of the temperature. So all of the heat that's evolved from this chemical change or absorbed is really just within that solution. So we assume that the calorimeter is not absorbing any temperature or any of the energy, and we can do all of our calculations from there. So the heat that the surroundings either absorb or give off is equal to the mass of the contents of the calorimeter, the specific heat, and the delta T. So Q equals MC delta T. So the Q of the change within it equals the Q that's absorbed or emitted from the surroundings. So system equals surroundings for the heat loss equals heat gained.
Hey, that was my slide.
Oh.
So we have Q of the system, heat of the system, plus
I got excited.
The heat of the surroundings equals 0. So that one's going to be negative, one's going to be positive. They're going to have the same magnitude. And in this case, our Q of our system is the delta H of the reaction.
So if we know one, we know the other because they both add together to be equal 0. So that's how we're going to get to this delta H of reaction. So here's an example. So what's a delta H of reaction? What's the enthalpy change of the reaction in kilojoules per mole of zinc? So it's going to be important when we figure that out. But so we're starting out with a 10.5 gram mass of zinc, and we're adding it to hydrochloric acid in our coffee cup calorimeter. So we're starting out, our acid is initial temperature of 19.7. After we add the zinc, the highest temperature that it reaches is the 23.4. So there's our change in temperature. There's our delta T. And the Q of the surroundings, now this is our system. So the Q equals Q. The surroundings is what's changing temperature. And that is a solution. So our zinc is dissolving in this HCl. It's actually reacting with it. So we have to have the mass of the zinc plus the mass of the HCl as our surroundings Our specific heat is provided, so we're assuming that it's not any different than the specific heat of water. It's dilute enough, and we have our temperature change from our experiment. Once we can solve for this MC delta T, that's Q of the surroundings. The opposite sign of that will be the delta H of reaction. When we solve this, it is in the energy unit of our specific heat. So everything else cancels and we're left with joules. So when we solve it, we're going to be in joules, but we need kilojoules per mole. We'll need another step to convert joules to kilojoules. And now per mole of what? Per mole of zinc. So that's what reacted. So you're going to need to take your mass of zinc, convert it to moles, and divide. So let's show you how we do that.
Okay, so you can see up in the top right in the red, we took our mass of our zinc and got the molar mass from the periodic table. 1 mole is 65.38 grams. So we have 0.1606 moles of zinc. We left a couple extra significant figures in there because this isn't our final answer. So we've got our equation written out here, the mass of both the zinc and the HCl, because that makes up the solution, and we're doing the MC delta T of the solution. We have to sum those two masses. We're using 4.184 for the specific heat, and it's delta T is final minus initial. So we've got 23.4 minus 19.7. We set that equal to 0. So when I do my subtraction and then multiply those three together, I get 1710.6. All the units cancel except for joules. So I've got delta H reaction plus 1710.6 equals 0. I need to get delta H reaction on one side of the equal sign. So I'm going to move that value to the other side. So I'm going to subtract it from both sides, leaving me with a delta H of reaction equal to a negative value, exothermic, and this is 1710.6 joules. The conversion to kilojoules, 1 kilojoule per 1,000 joules, is shown right here, and then we're going to divide by that number of moles of zinc. We're going to get a value on our calculator that's probably a lot of numbers, and we'll go back to our measurements and see that we should record this to 3 significant figures consistent with the mass, the temperatures, the mass and the temperatures. So our value is going to be 10.7 kilojoules per mole.
Negative. And the negative means it was exothermic. So does that make sense? If the reaction was exothermic, it would give off heat. And where would the heat go? Into the solution. And the solution's temperature would rise. Yes, it does make sense. We started out at nearly 20. We went up to just past 23. Increase in temperature, it must have absorbed energy, which means that the reaction itself gave it off. Here's your practice problem. Not sure why that's there. It's okay.
Okay, again, we're going to go to kilojoules per mole. So you're going to want to convert your mass to moles. We're adding this to water. This looks like it's a dissolution. It is enthalpy of dissolution. It says it right in the question. So we're going to dissolve the lithium chloride into the water. So our solution is going to consist of both the mass of the water and the lithium chloride. And there's a temperature decrease. Interesting.
Mm-hmm.
Interesting. So the delta T is going to be negative 5.8.
Yes.
Okay.
So your delta H should be the opposite.
There's your clues. Pause the video. Give this one a try. We'll show you the results in just a second.
All right. So here's your answer. And we talked about, just wanted to point out here, the temperature decrease of 5.8. That is your delta T. That's not we didn't give you initial and final. It said, okay, we started out with 18.4, but it says it decreased by this 5.8. So we don't have a final temperature. We have a delta T.
And we know that it's negative because the temperature went down.
Right. So here's your negative here with the 5.8 went down. And yeah, so the solution absorbed energy, right? No, it decreased. It gave off energy to this reaction or to this dissolution, which was endothermic.
You know, I see a possible problem here because our temperature decrease, our delta T, was just 2 sig figs. So I think technically here we should report that as 5.2 kilojoules per mole.
Could be.
Edit that.
Could be.
No one's looking. No one's looking.
Oh, 5.2.
5.2 kilojoules per mole. All right, hope that was helpful. Thanks for watching. Stay tuned. More to come. More thermochemistry.
More thermochemistry coming up next.
Bye.
Bye-bye.